Hello and welcome back. In this slice of physics, I'm going to serve up another free fall example. We'll now take a look at a ball that's tossed up in the air rather than being dropped down as we did the last time. Here's the specific problem we're looking to tackle this time. Henry tosses a ball straight up with a speed of 30 meters per second from a height of 1.5 meters above the ground. What maximum height above the ground does the ball reach, and how long does it take to reach this height? So let's see if we can draw a picture as usual and capture a lot of this information in that picture. So here's my ground level, and here's the height from which Henry tosses the ball up. And it's given to us that this height is 1.5 meters. And it says that he tosses it straight up with a speed of 30 meters per second, which gives me an initial velocity of plus 30 meters per second. And once the ball is released, it's going to move up, slowing down as it gains more height, and eventually it'll momentarily come to a stop before it falls back down and gains speed, eventually hitting the ground. Now, as we said in the last video, it's very important to define our initial and final moments of time that we are interested in. And in this case, my initial moment is when the ball was just barely released by Henry at a height of 1.5 meters above the ground. And the final, since I'm interested in the maximum height the ball attains right there and the time it takes to get there, my final position is right here. Okay, once I have framed all of this, we can now pick our coordinate axes and move forward in solving this problem. Once again, in this case, the axis that's relevant is our y-axis, and rather than show it directly on the ball, I'm just going to show it here, and even though I don't need the x-axis, I'm going to show it as the horizontal. So here's the segment of motion I'm interested in solving, and so let's start listing some of the things that we know about that. So I've got a vyi of plus 30 meters per second. Velocity in the vertical direction is pointing up. My y-axis points up, and that's why it's positive. What's my vyf? Do we know that? Well, since my final point is the maximum height the ball reaches, and we know that at the very maximum height the ball stops for a moment of time, that is my final situation. So my final velocity is going to be 0 meters per second in this case. And I also know my ay, which is minus g, which is minus 9.80 meters per second squared. Negative because the acceleration due to gravity points straight down, and my y-axis positive value points straight up. And the two things I'm being asked for are the height above the ground that the ball reaches. So this height is what I'm being asked for. And you can probably see that I can't solve for that directly with my motion segment, but once I get delta y for my motion segment, which is the height from I to f over here, I can then add the 1.5 meters here to get the h, and then finally I can get the time it takes to get there. Folks, let me just stop here for a second and emphasize what we just did in the last couple of minutes is the crucial part of solving physics problems. What happens after this is pretty mechanical, but if we try to skip this and go directly to equations, we end up making a lot of mistakes. So when you're working with physics, please emphasize the setting up and understanding of the situation as we have done here. So now I've included the 4 equations of constant acceleration motion, which is what free fall is all about. So in order to solve for h, I've got to first solve for delta y. So let's do that. I've got delta y, the pseudo of delta x in this equation over here. That's defined in terms of the initial velocity, time duration. I don't have time duration, so I can't use this equation. So moving on, I've got delta x in this last equation. I know my acceleration, I know my initial velocity, I know my final velocity. So this is the right equation to use in this case. So let's set that up. My equation says vyf squared equals vyi squared plus 2 times ay times delta y. So now, putting in the values, my VYF is 0, so that makes it 0 squared equals VYI is plus 30, square that, plus 2 times AY is minus 9.80 times delta y. Now I can do some simple algebra and move these terms around to get minus 19.6 times delta y equals minus 900. And so delta y becomes minus 900 divided by minus 19.6. The minuses cancel, and your calculator will give you an answer of 46 meters down to the 2 significant digits that we are interested in. So that's delta y, but we're not done yet. So we were being asked for h, the height above the ground that the ball reaches. So our h in this case would be the delta y plus 1.5 meters that it was launched from. So that gives us 46 plus 1.5, which is 47.5 meters. Again, rounded to 2 significant digits. That's going to be 48 meters. So that's the height above the ground that the ball will reach. Now to get the time it takes to get there, we can use this second equation over here. We know VF, we know VI, we know A. We can solve for delta T. We can also use the third equation now that we have delta Y and know everything else here, but that's more complex. We'll have to solve a quadratic equation in T. So it's always good to choose the simpler route. So let's use the second equation. So in our case, that equation is VYF equals VYI plus A times delta T. And so now putting in the values, I've got 0 equals plus 30 for VYI plus minus 9.8 times delta T. I'll let you do the algebra to move the terms around, and this equation will simplify to delta T equals 30 divided by 9.8, which down to 2 significant digits would be 3.1 seconds. So there we have it. We got the 2 answers we were after. So this slice of physics gave you a little bit more practice with free fall motion by looking at another example of a ball tossed up in the air. Thanks for watching.